All right, in Unit 8, we're going to be studying a topic known as continued fractions, and we're going to start with the most direct application of continued fractions, which is in the study of rational numbers. So let's start off with some preliminaries. We've never actually used a number in this course so far that wasn't an integer, and we're going to start doing so now. So a formal way to derive what the rational numbers are from the integers is not really what we're after. Instead, we're just going to rely on the fact that anyone who's taking this course or watching these videos knows what rational numbers are. A rational number is a ratio of two integers, a over b, where the denominator b is not equal 0. The set of all rational numbers is denoted with this q. The integer a is called the numerator and b is the denominator. A over b and c over d are equal exactly when a times d equals b times c as integers. Now, all the familiar rules of algebra like commutativity, associativity, multiplicative inverses, additive identities, etc., they all hold. Specifically, provided the denominator b is not 0, setting the greatest common divisor of a and b equal to d, where a is equal to a prime times d and b is equal to b prime times d, then a over b is equal to a prime over b prime. In other words, you can cancel out a shared factor from numerator and denominator. So similarly, we're going to consider a over 1 to be equal to just a, so that the integers can be considered to be a subset of the rational numbers. On a formal axiomatic level, they're technically not, but they are embedded by an injection into the rational numbers in a very natural way. Now, also observe that a over minus b is the same thing as minus a over b, so the standard form of a rational number, a over b, is to satisfy that the numerator and denominator are relatively prime and that the denominator is positive. This is standard form to have a positive denominator. So our first theorem, for every rational number a over b, there is in fact a unique integer q, so that q is less than or equal to a over b, which is less than q plus 1. Indeed, all we have to do is apply the division algorithm to say that a, the numerator, is b. Remember, in standard form, that denominator b is positive. So we can take the division algorithm and do a over b, and then plus the remainder, a remainder by b. So since the remainder is bigger than or equal to 0, we have that b times this quotient a over b is less than or equal to a. In other words, the quotient a over b is less than or equal to a over b, but similarly, the remainder is strictly smaller than b, meaning that a over b is strictly smaller than this quotient plus 1. In other words, the integer claimed by the theorem is exactly the quotient a over b. The quotient a over b is called the integer part of a rational number a over b, and the difference between the two is the fractional part a over b. So the fractional part of a over b is just the number a over b minus its integer part. Okay, so let's start working through some simple arithmetic and see some interesting things that happen. Our last observation just reminded us that the division algorithm is a thing. Specifically, 1 over a over b is equal to b over a, provided a and b are both non-zero. Also, if a over b is larger than 1, then b over a is less than 1. Again, these are all familiar rules of arithmetic. I don't want to spend too much time justifying them, just reminding us that this is how things work. So suppose that a over b is a rational number. Denote by a naught the integer part a over b. So a over b is its integer part plus its fractional part, which we're denoting by psi naught. Okay, so psi naught has to be a rational number because a over b is rational and it's equal to an integer plus psi naught, but it's this fractional part, a number minus its integer part, that's between 0 and 1. If psi naught is 0, do nothing. Otherwise, it's less than 1, so 1 over it is bigger than 1, meaning I can write 1 over psi naught as its integer part plus some new fractional part, psi 1. And similarly, this remainder, this fractional part, is between 0 and 1. Let's denote a sub 1 to be this integer part, 1 over psi naught. Continue this procedure. If you ever get a remainder, a fractional part being 0, just stop the procedure. Otherwise, if you have this next remainder or fractional part, just find the next one by taking a reciprocal and subtracting an integer part. And denote the integer part that you subtracted as a subscript n plus 1. So let's do an example, and we're actually going to see that this is quite a familiar algorithm. Let's suppose we start with 42 over 16. The integer part of 42 over 16 is 2. That's how many times we can take a 16 away from 42. Meaning that the first remainder or fractional part is 42 over 16 minus that integer part. 42 over 16 minus 2 is 10 over 16. I'm not bothering doing any simplification between the non-relative primality of the numerator and denominator, just to emphasize that it doesn't really matter. So next we can set a1 to be this fractional part of the reciprocal, 16 over 10, which is 1. Then the next remainder is the new fractional part, 1 over x naught minus the integer part we just computed, so 16 over 10 minus 1, or 6 over 10. Then a2 is the integer part of the next reciprocal. So having gotten 6 over 10, we reciprocate it, 10 over 6. The integer part of that is 1. That's how many times 6 goes into 1. And then the next remainder or fractional part is 1 over xi naught, the fractional part thereof. So 10 over 6 minus the integer part we just subtracted. 10 over 6 minus 1 is 4 over 6. We can keep going because we haven't hit a 0 yet. So a3 is the integer part of 1 over xi2, which is 1. The next remainder is 1 over xi2 minus that integer part we just computed, or 2 over 4. Next, a4 is the integer part of that reciprocal 4 over 2, which is 2. But now observe that the fractional part, 4 over 2, minus the integer part we just computed, is actually 0, so we terminate the algorithm. So we computed a0 is 2, a1 is 1, a2 is 1, a3 is 1, and a4 is 2. And now we stop because we have a 0 remainder or a 0 fractional part. So for a starting rational number a over b, this quote new end quote algorithm is really just computing successive quotients. Reciprocating the remainder allows us to compute a new quotient, reversing which number is on top versus on bottom. In other words, we're just executing the Euclidean algorithm again, computing quotients and then swapping the place of the two numbers. Specifically, for any rational number, this algorithm will terminate. But there's actually more. For our example, 42 over 16, we computed in order a0 is 2, a1 is 1, a2 is 1, a3 is 1, and a4 is 2. And observe, 42 is that first integer part 2 plus 10 over 16. But 10 over 16 I can rewrite as 1 over 16 over 10, but then we computed 16 over 10 was 1 plus 6 over 10. And then we can write 6 over 10 is 1 over 10 over 6, and 10 over 6 was 1 plus 4 over 6, and 4 over 6 is 1 over 6 over 4. And 6 over 4 was 1 plus 2 over 4, which is 1 over 4 over 2, which was 2 with a remainder of 0, and here's where we stopped. In other words, what we really computed is that 42 over 16 can be represented as this terribly nasty looking iterated fraction, 2 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 2, stop. And observe this is a0 plus 1 over a1 plus 1 over a2 plus 1 over a3 plus 1 over a4. So let's try to formalize the observation we made in that previous example. Let a over b be a rational number, set a0 to be the integer part or the quotient a over b, and set c0 to be the fractional part or the remainder a over b. And then recursively define an as, if the previous remainder or fractional part was 0, stop the algorithm, otherwise reciprocate it and compute an integer part, and have the fractional part of that reciprocal be the next remainder. Then the algorithm will terminate after finitely many steps. If the algorithm terminates at term a sub n, then a over b can be written as this iterated fraction a0 plus 1 over a1 plus 1 over a2 ... all the way down to plus 1 over an. Furthermore, all of the ai's that we compute, all of the integer parts, are bigger than or equal to 1, except perhaps the very first one, a sub 0. So the proof is pretty straightforward. We already covered the fact that the algorithm terminates. That's the Euclidean algorithm. The fact that the two sides are equal to each other follows from the fact that the algorithm terminating at an implies that that remainder is 0. So 1 over cn minus 1 is simply flat out equal to the integer part an. And then you just sort of recursively work through this process and construct this iterated fraction. The fact that all of the ai's are bigger than or equal to 1 comes from computing these integer parts. So our remainders are always positive. If they're not 0, because the remainder was less than 1, then its reciprocal is larger than 1, meaning the integer part, is also bigger than or equal to 1. The only exception is the number we started with, a over b, might have a negative integer part, a sub 0. So let's define some notation. From the previous slide, what we have is what's unsurprisingly called a continued fraction expansion. The notation can be a little unwieldy to write this fraction within a fraction within a fraction and have all these ellipses everywhere. So if you have this iterated fraction procedure, we write it as a naught semicolon, a1 comma a2, etc. up to an. The a naught set apart by the semicolon is the only possible negative entry, and it is the integer part of the number you started with. So a common step, if one is studying continued fractions, is to observe that up to adding or subtracting an integer, you may as well assume that the integer part is 0. In other words, that you're only looking at numbers between 0 and 1. In other words, a sub 0 is 0. When a sub 0 is equal to 0, it's quite common to simply leave that term out entirely. In other words, don't even write the 0, just write brackets around a1 comma a2 and etc. up to an. I'm not going to do that, but it is extraordinarily common. I don't even think it's potentially confusing. There are a lot of very good reasons why one tends to restrict the study of this to simply the interval 0 to 1, in which case the term a naught is irrelevant anyway. But for the purposes of our work and in the videos and lectures I'm recording here, I'm going to keep including a sub 0 with that semicolon. The numbers ai are called partial quotients. They were in fact computed in the division algorithm as quotients, so we call them partial quotients of the number we started with. So what if we tried to do the other direction? In other words, we start with a continued fraction expansion and we want to know what rational number would have generated it. So for example, suppose we have the continued fraction 0 semicolon 3152. What rational number does that represent? So what we have here is 0 plus 1 over 3 plus 1 over 1 plus 1 over 5 plus 1 over 2. So what we're going to do is we're going to work from the end back towards the beginning, computing successive remainders. So 5 plus 1/2 is 11 over 2, meaning that 1 over it is 2 over 11. So now we have 1 plus 2 over 11. Well, 1 plus 2 over 11 is 13 over 11. So 1 over that is 11 over 13. 3 plus 11 over 13 is 50 over 13. So 1 over that is 13 over 50. So the number we started with is 13 over 50. Now, for reasons which will become clear later, we don't actually want to compute these things by starting with the last term and working back towards the first. What we want to do is start at the beginning and work forward. So suppose the partial quotients are given by a naught, which can be any integer, possibly negative, but after that, a1 through an are all positive integers. There's a supplementary video that you can find here. Hopefully I put up the little card with a link. Okay, a supplementary video that shows the value of this continued fraction can be computed from the beginning forward as Pn over Qn, where Pn and Qn are computed through recursively defined sequences. P0 is simply equal to A0 and Q0 is always equal to 1. P1 is always equal to A0 times A1 plus 1, and Q1 is equal to A1. And then, if you want to compute P2 over Q2, P3 over Q3, and so forth, Pi is always given by the partial quotient ai times the previous numerator plus the previous numerator before that, and Q, similarly, is the partial quotient ai times the previous denominator plus the denominator before that. So the recursive formula is actually the same for both sequences, but they do differ in their initial terms. Okay, so we have the same recursive formula here where 1p, one numerator, is a partial quotient times the previous numerator plus the numerator before that, and the next denominator is a partial quotient times the previous denominator plus the denominator before that. That's the same. However, they start with different values, a0 and 1, and a0, a1 plus 1, and a1, respectively, for p1, for pi, and qi for I equals 0 and 1, respectively. So the numbers pi over qi are called the convergents of the number you are computing. When a0 is equal to 0, observe that p0 is just 0 and p1, a0 times a1 plus 1, is just 1. So in the world where a0 is generally assumed to be 0, these are a little simpler to compute at the beginning. So here's the example we did. The continued fraction 0, 3152, was equal to 13/50. So let's compute Pn over Qn working from the beginning forward. So P0 is A0, which is 0. Q0 is always 1. P1 is always A0 times A1 plus 1. So we have 0 times 3 plus 1. That's just 1. Q1 is always A1, which is 3. Now, we've established P0 over Q0 is 0 over 1, P1 over Q1 is 1 over 3. Now we can start using our recursive formula, and since our continued fraction ends at index 4, we have A0, A1, A2, A3, A4, so the last term is 4. Once we've computed P4 over Q4, we'll be done. So P2 over Q2, we use the same recursive formula for both, is A2 P1 plus P0 over A2 Q1 plus Q0. Looking at the original continued fraction, A2, the second partial quotient, is 1. We computed P1 is 1 and P0 is 0, Q1 is 3 and Q0 is 1. So we plug those in, we get 1 times 1 plus 0 over 1 times 3 plus 1, or 1/4. Next, P3 over Q3. Well, the partial quotient A sub 3 is 5. We've already computed P2 and Q2, so we have 5 times 1 plus 1 over 5 times 4 plus 3, so 6 over 23. And finally, the term we were actually interested in, P4 over Q4, we find our fourth partial quotient is 2. We've already computed both P3 and P2. We plug them in, we get 2 times 6 plus 1 over 2 times 23 plus 4, or what we already knew the answer was going to be, 13 over 50. Okay, so any rational number generates a list of partial quotients, and we can represent that as a continued fraction. And also, any list of partial quotients, we can compute a rational number that equals it. Is this association injective? Can we make a unique correspondence between lists of partial quotients and rational numbers? No, but it's close. Ultimately, what we're going to show is that every rational number has exactly 2 ways to represent it as a continued fraction. It will take a few steps to get there. It's not going to be the most straightforward, but it's a nice little observation and it gets us very familiar with working through the terminology and notation of continued fractions. Okay, so first, suppose we have a generic integer for a sub 0 and positive integers for our other partial quotients. Let pi over qi be the convergence as we've previously discussed. P0 is A0, Q0 is 1, P1 is A0, A1 plus 1, Q1 is A1, and then past that point we have the same recursive formula for both. So here's our theorem. Consecutive pi and qi are always relatively prime for one another. Specifically, the greatest common divisor between 2 consecutive p's and the greatest common divisor between 2 consecutive q's is always 1. So it's just a pretty straightforward inductive proof. When I is 0, P0, P1 is A1 and A0, A1 plus 1. If you apply the Euclidean algorithm once, you'll get that the greatest common divisor is 1. Similarly, with Q0 and Q1, you get 1 in A1, and the greatest common divisor of 1 in anything is 1. Okay, so there's our base case. When I is 0, P0 and P1 are relatively prime, Q0 and Q1 are relatively prime. So let's assume that 2 consecutive partial quotients are, not partial quotients, but numerators, are relatively prime. Then the Euclidean algorithm yields that pi plus 1 pi, well, pi plus 1 is simply ai plus 1 pi plus pi minus 1. And we're taking the GCD of that with pi, but if we apply the Euclidean algorithm, okay, so all we've done is use the recursive formula here. And when I apply the Euclidean algorithm, I ask how many of these pi's can I subtract from this? Well, exactly ai plus 1 of them. And when I do, I'm left behind with pi minus 1 pi, and inductively we have assumed that these two are relatively prime. So it's a very straightforward inductive proof that the consecutive numerators p are always relatively prime, and the qi's follow the same recursive formula. It's an identical proof. Okay, more than that, the p's and q's are relatively prime to each other. Okay, so specifically, pi times qi minus 1 minus qi times pi minus 1 is a power of -1, specifically -1 to the I plus 1. So any linear combination of two numbers being equal to plus or minus 1 by Bézou's lemma tells us that they're relatively prime. So any linear combination of the two numbers must be a multiple of the GCD. And if plus or minus 1 is a multiple of your GCD has to be 1. Okay, so for I equals 0, P0 is A0 and Q0 is 1, and the GCD of A0 and 1 is equal to 1 quite trivially. For I larger than or equal to 1, we will prove the stronger result that we can find a linear combination equal to plus or minus 1. Now for I equals 1, let's look specifically at P1 Q0 minus Q1 P0. Well, P1 is always A naught A1 plus 1, Q naught is always 1, Q1 is always A1, and P naught is always A naught. And what do we end up? With the A naught A1s cancel, and we just have a 1, which is negative 1 to the second power. This matches our listed form. So now let's assume that the result holds for some value of I. We're going to compute the difference for the next index, first using the recursive definition of both pi plus 1 and qi plus 1. Okay, so pi plus 1 times qi minus qi plus 1 times pi. We use the recursive definition to say that pi plus 1 is ai plus 1 pi plus pi minus 1, and qi plus 1 is ai plus 1 qi plus qi minus 1. Some terms, if we distribute this whole thing out, will cancel. For example, ai plus 1 pi qi, ai plus 1 qi pi with a minus in between will cancel. So some stuff simplifies, and all that's going to be left behind is pi minus 1 qi minus pi qi minus 1. That, if I factor a minus sign out, is exactly what we will have made an inductive assumption about. So that's negative 1 to the I plus 1, which is simply negative 1 to the I plus 2. So assuming the desired formula holds at a given index, we've shown that at the next index you simply multiply by minus 1, but we're trying to get consecutive powers of minus 1 anyway, so we get exactly what we want. Now, as a corollary to this, the difference between two consecutive convergents, pi over qi and pi minus 1 over qi minus 1, is always 1 over the product of the denominators. It's a very straightforward proof. If you give this a common denominator, what would the numerator be? Pi q minus qi minus 1 minus pi minus 1 qi, which is exactly a power of minus 1. And since we're an absolute value, that's just going to be a 1. Okay, now our goal is to show that one rational number can be represented exactly two ways as continued fractions. We're continuing to build towards that result. That is our goal. So first what we'll do is we'll show there are relatively few ways to represent integers as continued fractions. Specifically, suppose n is bigger than or equal to 2, and we have a continued fraction expansion that goes out to index at least 2. That is never an integer. Now, since a naught is an integer, this represents a naught plus a bunch of stuff here. So ignoring that, setting the first term equal to 0, in other words, we just want to show that this cannot possibly be an integer. So let's proceed by induction, and our base case is 2. Well, a1, a2, if you simply compute what this is, it's 1 over a1 plus 1 over a2, or p2 over q2. But those are relatively prime. So p2 over q2 can only be an integer. There's no cancellation to be done because the two are relatively prime, so the only way it can be an integer is if the denominator is exactly 1. But a1 and a2 are positive integers, so this denominator, q2, is at least as large as 2. So this can't be an integer. So let's assume for some n bigger than or equal to 2, and any possible list of partial quotients, any expansion of length n can't be an integer. Okay, so we want to prove that any expansion of length 2 or bigger can't be an integer. So let's consider an expansion of length n plus 1, having inductively assumed that an expansion that ends at the index n, it can't be an integer. So what we have here, if I go from a1 to index n plus 1, here's our lengthy way of writing it as a continued fraction, but observe, this is 1 over a1 plus, and now what's this fraction right here? That's just 1 over a2 plus 1 over a3 all the way to that. This is now a length n expansion. It starts at index 2 and ends at index n plus 1, meaning it has exactly n terms in it. But our inductive hypothesis was that no continued fraction expansion of length n could possibly be an integer. So this is not an integer here. Therefore, a1, which is definitely an integer, plus this can't be an integer. And I have 1 over that, so that's not an integer. So we've inductively proved that if a length n expansion cannot be an integer, then a length n plus 1 expansion cannot be an integer, and we've shown a length 2 expansion can't possibly be an integer, so inductively no expansion of length 2 or larger could possibly be an integer. Continuing, any continued fraction expansion with length at least 2 and integer part 0 is strictly in between 0 and 1. Specifically, if we have a length 2 or larger expansion with a 0 integer part, it's not equal to 0 and it's not equal to 1, and it must be in between. Furthermore, the only expansion of length 1, again under the assumption that a0 is 0, that could possibly be an integer, is setting a1 equal to 1. Now observe, if you just had an a1 in there, that would just be 1 over a1. So if you set a1 equal to 1, 1 over 1 is definitely an integer. That's immediate and there's nothing to say about it. But for the first claim, let's induct on n. So we need to establish that the 2-length continued fraction a1 comma a2 is between 0 and 1. We simply compute it. It's p2 over q2, which is just going to work out, since a0 is 0, to be a2 over a1 a2 plus 1. All terms are positive, so this is definitely a positive result. a1 is a positive integer, so the denominator is strictly larger than a2, so the result is less than 1. It's between 0 and 1. Now let's assume the result holds for all expansion of length 2 or larger and consider some expansion of length n plus 1. We do the same trick we did before. This length n plus 1 expansion is 1 over a1 plus 1 over all of this. So we just assumed that that second term there is between 0 and 1. So now what we have is we have 1 over a positive integer plus something between 0 and 1. So 1 over a non-integer that is bigger than 1. 1 over that is therefore less than 1, but everything is positive. So what have we done so far? Not a whole lot. Any continued fraction expansion that has an index 2 partial quotient is not an integer. Let's suppose I have 2 continued fraction expansions. I call them x and y. Let's suppose x equals y as numbers, but the continued fraction expansions are not identical. So there is a first partial quotient where I see a difference. So there is a first index I where ai is not equal to bi. We can actually assume that's right at the beginning. So in x, we have a0 plus 1 over a1 plus 1 over a2 dot dot dot. Out to a certain point, let's say 1 over ak plus star. And then suppose y starts with the same partial quotients, a0 plus 1 over a1, all the way out to plus 1 over ak, and then I start to see a difference. Well, since the first few partial quotients were the same, what remains by computing just the tail end starting at the first difference must produce different numbers. Otherwise, we would have exactly the same continued fraction expansion, and if they produced the different numbers, we'd have x not equal to y. So because x does equal y, we may as well ignore the first several terms that happen to be identical and focus just on starting the continued fraction expansion at that first term where there is a difference. So let's assume that a0 is not equal to b0. Furthermore, let's just assume that a0 is the bigger one. If the two numbers are different, one of them is bigger than the other. So let's say a0 is larger than b0. If I subtract the integer b0 from both numbers, we may as well assume that b0 is 0 and a0 is positive. Okay, so now we can make a very strong restriction. Suppose I have 2 continued fraction expansions, a0 and so forth, is equal to 0 and then partial quotients bi, where a0 is positive. The only way this can possibly happen, having a positive integer and then stuff, equaling 0 and then stuff, where that has to be positive here, is if n is 0. In other words, this continued fraction expansion actually doesn't have anything beyond the integer part a0. This continued fraction expansion has exactly one more term. Okay, so the length here, the final index, is exactly 1, and that one term that appears must be exactly 1. So we can verify that when all of those things happen, the initial hypothesis does hold. Okay, so suppose I had a 0 followed by a 1, and then I stopped because I stop at index 1. That'd be 0 plus 1 over a 1. That's just 1, which is the same thing as if this started with a 1 and then had nothing else. 1 plus, well, plus nothing, just 1. So these happen to be equal, even though they are not identical continued fraction expansions. That's something we can easily just check. The real work of this theorem is to show that that's the only possible way 2 finite continued fraction expansions could possibly be equal, where this one begins with a 0 and this one begins with a positive integer. The only way that can possibly happen is to have this specific selection. Okay. So let's assume the 2 continued fraction expansions are equal as numbers. One of them begins with a positive integer and one of them begins with a 0. So a0 plus 1 over a1, etc. is 0 plus 1 over b1 all the way out to 1 over bm. Okay, I can solve this for a naught. But a naught, by assumption, was a positive integer. In other words, this continued fraction, observe that we don't have an integer part here, so there's no semicolon. This continued fraction minus this one is equal to this positive integer. However, if m and n are both bigger than or equal to 2, we've established that these can't be integers. They are between 0 and 1. So I would have a number between 0 and 1 minus a number between 0 and 1. The furthest apart they can be is strictly less than 1, so the difference is definitely not the positive integer a naught. So we've concluded that m and n cannot both be larger than or equal to 2. So one of them has to be 1 or 0. Suppose m is equal to 1. Okay, so this continued fraction expansion ends here. If m is 1 and b1 is bigger than 1, you would still have that b1 ... out to bm. Well, that would just be the single term bm or b1, doesn't matter because m is 1, remember. If this number is larger than 1, you have 1 over that, strictly between 0 and 1. So more specifically, if m happens to be equal to 1, b1 has to be 1, or maybe n is equal to 1, in which case a1 has to be equal to 1 for the same reason. Okay, we need to have the difference of these two things be a positive integer, so I can't have them be numbers between 0 and 1. Okay, so if we assume the hypothesis of this theorem, what we've derived is that this continued fraction minus this one is a positive integer. The only way these two continued fractions that don't have, note, an integer part on them, the only way their difference can be a positive integer was the length of this expansion is exactly 1 and it ends in a 1, or this one ends there and also ends in a 1. Now if n is equal to 1 and a1 is equal to 1, then this continued fraction expansion is just 1 over 1, which is a positive integer. But b1 all the way up to bm cannot be larger than 1. It's a continued fraction expansion 1 over b1 plus etc. So the only way this could also be a positive integer is for m equal 1 and b1 equal 1. So all that remains to prove is that n actually can't be 1, it must be 0. So we had to have m equals 1 and b1 equals 1. And 1 minus that must be a positive integer. Well, this here has to be empty. It has to be 0. There has to be nothing there, or just not there to begin with, however you prefer to think about it. That's the only way that 1 minus that continued fraction could be a positive integer, if it just wasn't there to begin with. So if the same value has two different continued fraction expansions, focusing on where the first index is different, we determined that the difference in the two partial quotients must be exactly 1. Remember, in our previous theorem, we subtracted our b naught to just make one of them a 0, and we derived the other one as exactly 1 larger, or just 1. So taking back that subtraction of b naught, wherever the first difference occurs, the two partial quotients must be apart by exactly 1. Also, where the smaller number occurs has exactly one more term in its expansion, and that next term has to be a 1. In other words, the only way two continued fraction expansions can be different but produce the same number is to have all the same initial terms. Where there's finally a difference, they differ by exactly 1. Whichever one is larger stops. Whichever one is smaller has exactly one more term, which is 1. This works, by the way, if an is larger than 1. Otherwise, you couldn't subtract 1 from it. If an happened to be equal to 1, well then, the previous term is where you had the extra plus 1, and then that continued fraction stopped. So every rational number has exactly two ways it can be represented. One of them ends in a 1, and the other doesn't, where an is bigger than 1. Or if an happens to equal 1, this expansion ends in a 1, and this one is a positive integer plus 1, so it's definitely not 1. So every rational number has a continued fraction expansion that terminates, and then there are exactly two finite length continued fractions that represent the same number. One of them ends in a number larger than 1. The other one, subtract 1 from that and tag on a comma 1, and you'll end up with the same value. Now there is an overwhelming convention here. So the standard way to represent a rational number with its continued fraction expansion is do not take the representation that ends in a 1. So for 13 over 50, we found continued fraction expansion 3152. This is equal to, this number is bigger than 1, so subtract 1 from it and then tag on an extra 1. This will produce the same number. These two are the same number. But this is the standard way to write it. Do not end a continued fraction expansion with a 1. So similarly, this continued fraction expansion, whatever it is equal to, is totally legitimate, but it happens to equal a 1 at the end, its last partial quotient. So the more standard way would be to take this 1 and absorb it into the previous term, 3, 4, 1, 5, 1, 10. This way of sort of shifting a 1 back and forth only works in the last index, by the way. In general, you cannot just move numbers in a continued fraction expansion. We'll get more into that later. We only showed this works if that is where the continued fraction expansion ends, hard cut, full stop. Now, the convention for generation of partial quotients through the division algorithm also respects this. You always pick the largest partial quotient you can. In the division algorithm, you pick the biggest quotient you can. There are limited scenarios, however, where other conventions happen to be convenient. So sometimes, of the two possible expansions, observe that one of them has exactly one more term than the other. So whatever rational number you have, it has two continued fraction expansions. One of them ends at an even index and one of them ends at an odd index. Sometimes it's convenient to assume that it ends at an even index, or sometimes it's convenient to assume it ends at an odd index. So we might prefer this expansion because it ends at A0, A1, A2, A3, A4, A5, A6. And maybe we're working on a problem where we want to assume the last partial quotient has even index. So maybe this is more convenient than this, which ends at an odd index. Or maybe the other way around. But absent any concerns like that, the overwhelming convention, if you talk to people, is assume that the last partial quotient isn't a 1. It's worth pointing out, by the way, that the exception to this is if x happens to equal simply the number 1, you represent it as 1 as an integer part with no continued fraction expansion after that. So technically, that is an expansion that ends in a 1, but its alternate form would be exactly this, which also ends in a 1. And we don't take this one, we take this one. So, okay, there's a single number where you are forced to end in a 1, but you do so in the integer part, not in the continued fraction part.